Hello, my name is Gregory Duthé. I'm a PhD student at the chair of Structural Mechanics and Monitoring at ETH Zurich. On behalf of my colleagues Abdallah and Chatzi, I will be talking about our work on modeling and diagnosing the degradation of wind turbine blades due to leading edge erosion. So to start off, let me start by giving you a bit of background. As a part of the AeroSense research project, we are currently developing a MEMS-based aeroacoustic measurement system. This system will be placed on wind turbine blades and will allow us to do structural health monitoring tasks. Specifically, our system will measure the pressure field along a section of the blade, and the behavior of this pressure field can give us important information on the blade's structural integrity, but also on its surface condition. Now, in this presentation, I will mostly focus on the relation between integrated pressure quantities, lift and drag, and the changes in surface conditions, namely leading edge erosion. So, what is leading edge erosion? Well, over the course of a wind turbine's operational lifetime, the surface condition of the leading edge of the blades is slowly degraded. And this is mainly due to environmental conditions such as rainstorms or temperature changes. It can, however, also be caused by manufacturing defects or installation or maintenance errors. The degradation worsens towards the tip of the blade where the relative wind velocity is higher. Leading edge erosion leads to a loss of function, and this entails a drop in the power production of the wind turbine. And this can be up to 5% for megawatt scale wind turbines. It also increases maintenance costs and noise emissions. Current methods to diagnose the extent of leading edge erosion rely on visual inspection, either manual or via drones, and both of these require turbines to be shut down. Another option is to do a statistical analysis of the SCADA data, where the SCADA is the supervisory control and data acquisition system. And however, this doesn't work that well, and it is very turbine dependent. So there is a gap in the spatiotemporal modeling and diagnostics of leading edge erosion for wind turbine blades. Our objective is twofold. First, we want to construct a model of the physical degradation process, and we also want to design an analytical system which can locate and classify the severity of leading edge erosion. Here I show a graphical abstract of our proposed method. I'll mainly be talking about the modeling aspect, but I will also give an overview of machine learning diagnostics methods, which are here in this black box. So to start off with building our model, we decided to take a look at an existing database of wind turbine blades with degraded leading edges. In this work by Serene et al., the features of the progressive degradation are captured and categorized. And they show that leading edge erosion starts off with small pits, which then coalesce together to form gouges. And if this is left untreated, the gouges accumulate and the degradation progresses to delamination, which can severely impact the aerodynamic properties of the blade, but also its structural integrity. So the authors of this paper devised this categorization, and they also performed wind tunnel tests of airfoils with various stages of leading edge degradation corresponding to these categories. They reported the impact of the different stages of leading edge erosion on the aerodynamic performance of these airfoils. And thanks to this previous work, we are now able to quantify the aerodynamic quotas for a given erosion class. Now, to properly model the progress and time of the degradation, we need to account for two things, namely the arrival rates of damage, but also the size of the damage increment when it arrives. And this information, we build our non-homogeneous compound Poisson process. And we use this model to we use this process to model the cumulative damage where our system is subject to shocks at random points in time. The rate of arrival of these so-called shocks is not constant, but actually changes in time as well. The damage increment that occurs on shock arrival is a realization of a random process, which is exponentially distributed. The algorithm used to generate these degradation paths is shown here in this pseudocode. Let me just move my picture here. And so on the right-hand side, we show an example of some degradation paths for a blade with 5 sections, where each color corresponds to a different section and therefore a different part of the blade which is undergoing its own non-homogeneous compound Poisson process degradation. And you can see that over the time, we have shocks that arrive, and each section follows its own path as and this is due to the randomness included in this non-homogeneous compound Poisson process. To get a good idea of how a blade would degrade, we would need to run this process many times, as one path is not enough. At the bottom here, I've shown how the lift coefficient of a section degrades over time. Now you can see that the degradation is more prominent at higher angles of attack where the lift coefficient is high. Now we can couple this non-homogeneous compound Poisson process with an aeroelastic simulation tool for wind turbines called OpenFast. And so the degraded polars are passed as parameters to the simulation, and given an input time series of inflow conditions, we obtain the simulated behavior of the wind turbine. From this behavior, we can actually extract a number of output parameters, for instance, bending moments, accelerations, deflection. And here I show some examples of outputs from the coupled aeroelastic simulation. In black, I plot a sample which is taken from the beginning of the degradation process, and in red, one which has already undergone years of degradation. And you can see that due to the inflow conditions being different, it is not that obvious how to tell apart the different levels of degradation. And it is for this reason that we feel that machine learning methods will be well suited for the diagnostics part of our problem. So when looking at the diagnostics part of the problem from a machine learning perspective, we can describe it as a stacked multivariate classification task. So we would like to predict the degradation class at multiple zones along our blade, given an input multivariate time series. And by stacked, I mean we have multiple classifiers, so we stack them to get each zone along the blade. So what kind of classifier should we use? Well, one option is to use a feature extraction method combined with a simple shallow machine learning classifier, such as support vector machines. And these feature extraction methods, I've listed 2 here, which are popular. Bag of pattern methods have been quite popular in recent times, and random convolutional kernels have this so-called rocket method has been shown to be quite effective. Now, of course, deep learning methods have completely and profoundly changed the machine learning scene, and including for multivariate time series classification. We could imagine using convolutional neural networks, which are well suited for computer vision tasks, to classify an image which is generated by embedding the time series, or even to use 1D convolutions on the raw input data. Another popular set of deep learning methods are recurrent neural networks. And for instance, long short-term memory networks, LSTMs, have been quite successful at these multivariate time series problems. But recently there has been quite a drastic shift towards transformers, which seem to be extremely capable at extracting relevant information from sequential data. So transformers were originally built and designed for natural language processing, and thanks to their powerful attention mechanisms, transformers are well suited to create links between relevant parts of a sequence while filtering out noisy signals. This could be especially interesting for structural health monitoring tasks. And we have opted to show here what a transformer architecture and workflow would look like. So first, we would take our input multivariate time series and pass it through a learnable filter to get an embedding. And added to that, we add a positional embedding. And the combined embedding is then fed into an encoder stack made of transformer modules, and the encoded output is then passed into a classification MLP. After that, we apply softmax per degradation zone to obtain the most likely degradation class in each zone. And in each layer of the encoder stack, multi-head self-attention is applied through a pretty standard transformer architecture that I show here. Now, I won't go into too much detail in this regard. So, to conclude, we have developed an algorithm which models the spatio-temporal degradation of the leading edge of wind turbine blades. This model was then coupled to an error-elastic simulation tool. And this allows us to simulate the behavior of a wind turbine undergoing this degradation over a long time period. The data from the simulation can then be used to train an inference machine learning algorithm, such as a transformer. It is, however, an ongoing challenge to calibrate the parameters of the non-homogeneous compound Poisson process with field data. But with a properly calibrated simulation, we can then test and validate a transformer network to detect, locate, and classify the extent of a degraded leading edge. So just a few words of acknowledgements. I'd like to thank the Bridge Discovery Program of the Swiss National Science Foundation and InnoSuisse for funding this research, as well as the European Research Council via the ERC starting grant Windmill for their support. Thank you very much for your attention, and I hope you have a nice rest of your conference, and I am open to any other questions that you may have.